All right, so there was a couple questions on the homework. So most is well, pretty much all of this comes from section 5.2. So here, let me check that out. All right, so 5.2, it's all about integration, especially using this natural log stuff. And then there's some trig stuff there as well. So I would highly recommend, if you haven't done so already, before you get too far into this homework, make sure you watch, obviously, section 5.2 video, but also on that video list, there's a basic trig integral a video. So you probably want to check that one out as well, okay? Because that kind of goes over some Calc 1 stuff, and then it also goes over basic trig integrals. So what am I talking about there is, you get that formula sheet out here. Let's talk about this first. All right. So remember, Calc 1 stuff, basic trig functions from Calc 1 as well here. But basically, that other trig video I was talking about, it also goes through how to integrate tangent all by itself, cotangent, secant, and cosecant all by itself, right? It walks you through where these come from. But in the future, you're more than welcome to use this integration sheet here, the formula sheet. So now, again, when you're talking about this integration formula sheet, it's one of those things where you don't want to have to rely on this sheet too much. It's more of a check, like tangent, cotangent, secant, cosecant. Remember, these are a little bit trickier than what we did in Calc 1 because we don't have a nice function whose derivative are these, right? And then you can kind of visualize, oh, tangent, remember that sine over cosine. Oh, the cosine in the bottom, that's why it turns out to be a natural log, right? Because of that whole derivative of natural log being 1 over the denominator. And so since the denominator of tangent, is the cosine, that's why it's a natural log, right? The same thing here. Cotangent is cosine over sine. That's why the inside here. Secant and cosecant are a little bit trickier. Again, if you watch that video, it breaks it down a little bit more, okay? But again, you want to know that these are all natural log, and if you can't remember, wait, is it natural log sine or cosine? I forget. That's what the formula sheet is for, right? I have no idea, and I hope it's on this magical sheet. Okay, so keep that in mind as you go through. All right, anyway, going back to the actual stuff here. The first question, I mean, there was some trig questions here, but there was a question about number 5. Now the numbers are a little bit different, but the basic idea here is you have this. Let me just show you the on number 5 here. It's a different fraction than the person who was asking about it, but it's the same basic idea. But their numbers were. Let me just write it down here. This. So it's 2x squared plus 2x minus 6 all over x minus 1. Okay. So now, as far as integration is concerned, back in Calc 1, remember, the only thing that we know how to integrate at this stage, is basic power stuff, right? Or some trig here. Now we've got this new thing here with when you have just a linear term on the bottom like this, we can use the natural log. Okay, so anytime, this is basically the only thing that's new here from Calc 2 so far, is when you see a linear term in the bottom, you can then use the natural log idea, right? Basically where the power rule failed. Okay, so how do I do that here? Well, the bottom is more complicated. And also, so what I'm saying is, like, if there was only an x on the bottom, then you could just distribute that one x into each one of those, and then you would have individual little terms. Some wouldn't, power rule after you're done here. This would just be easy. And then this one, you could use a natural log. The problem here is it's not just an x. It's a whole linear term, right? It's not only got the x part, but it's also got a constant part, okay? So when you don't have just one term like this, the thing you got to remember is the degree of the top here is 2, and the degree of the bottom is 1. Anytime the degree of the top is larger or the same as the degree as the bottom, you basically have to do the division. Since it's not one term, you can't just simply divide by each one. Since it's a multiple of terms, basically you got to do the long division, okay? So this is what's telling you, anytime the degree of the top is larger than the bottom, this is what's telling you long division in this case. Okay. Basically, think of it as kind of like an improper fraction, right? The top is larger than the bottom, so it's improper. So I got to get rid of that. So remember how you do long division. The bottom goes outside, and then the top goes inside. So this would be 2x squared plus 2x minus 6, right? And then it's usual long division stuff. I mean, it looks different, if you can't remember how to do this with polynomial things. But basically, you look at the first one here and the first one here, right? And you think, okay, I want x to go into 2x squared. How many times would that be? We'll go up here, just like normal long division. But you want to ask yourself, what would you multiply by to get to 2x squared? Well, number-wise, I got a 1 and a 2. So obviously I need a 2, and then I also need another x. So you'd have to multiply by 2x. And the reason why that works is because 2x times x is indeed 2x squared. And then the 2x times a negative 1 is a negative 2x. right? So looking at the first one and the first one here, what would you multiply by? And then make sure that you multiply by everything. Then, just like normal long division, you subtract. But that's basically going to change all your signs. So this is now going to turn to a negative, and now this would turn to a plus. And these would indeed go away, right? 2x squared minus 2x squared, right? That first column doesn't go away. You got the wrong thing up here. But here, 2x plus 2x is the 4x, and then you bring down the next term. And then you just repeat. So looking at the first ones again, what would you multiply x by to get to 4x? A positive 4. The 4 times x is indeed 4x, and the 4 times the 1 is negative 4. And you go back, change all your signs because you're subtracting, right? 4x minus 4x goes away. Good. Again, that same idea. You got the right thing up top because the first column went away. And then here, minus 6 plus 4 would leave you with a negative 2, right? So this would be your remainder. So basically, this goes into here, right? The x minus 1 goes into 2x squared plus 2x minus 6 this many times with this left over. Or basically, it's like you're creating a mixed number, if you will, right? So this is like the whole part, the 2x plus 4, plus then you're going to have the fractional part. You're going to have the negative 2 over the x minus 1. Maybe it might be worth doing just to show you what I'm talking about, like with numbers. Like, I don't know, let's say I had 726, right, for example, and I wanted to divide by 11, whatever, okay? So it's kind of the same thing. This is the thing I'm dividing into. This is the thing I'm dividing by, right? So 11 goes into 726, right? So 11 does not, but again, it's kind of the same thing here. You don't look at the whole number, just like here, you wouldn't look at the whole thing. You just look at the first part that it goes into, right? So the x goes into 2x squared. That's the first time it goes into something. Just like 11 goes into 72 6 times. And again, you don't just do 6 times 1. It's 6 times the 1, 6 times the 1, and 66. That's why you do it times both here. And then you subtract, change the sign. So 72 minus the 6 would be the 6. Bring down the 6. Oh, well, man, I just randomly picked a number. I didn't even mean for that to happen. I probably should not do that. Let's pretend this said 728. Okay, because the whole point here is 11 would go into 66 evenly. I don't want that. I want there to be the remainder. So let's pretend it said 728 the whole time. So you would bring the 8 down. Okay, so now 11 would go into 68 again 6 times. So 6 times 11 again would be the 66. Subtract, and you have a remainder of 2. Okay, so just like you would do with a normal improper fraction, you can write it as a mixed number, right? 11 goes into 728 66 whole times, plus the fractional part, which is the remainder over what you were dividing by, right? So it's 66 plus 2 11ths. Now, normally when you do mixed numbers, you don't write the plus. You just write them next to each other, right? But you can't do that here, right? You got to write plus, make sure. But if that same idea is, that's the whole part, that's how many times it goes in there evenly, plus the fractional part, which is the remainder over whatever you're dividing by, right? So that's what I have left. Okay, now we can integrate this. But again, it's that same trick of you're just creating individual little terms. This is old school Calc 1, right? Add 1, power rule, right? It's x squared divided by 2 is going to kill the 2. And this is just 4x. And this one is now you're back to that linear term on the bottom. Now, you got to watch out for that linear term on the bottom here. You can jump right to the natural log, but do watch for the derivative of that inside is 1 here, right? So you could jump right to, this is the negative 2 is going to come along for the ride, then it's the natural log of the absolute value of that denominator, but just make sure that you watch out for the fact that the derivative of that inside is 1, right? So I don't need to adjust. Because if there was something more complicated, you would need to adjust that. And then since this is improper, tack on a plus c. And there you go. All right, so the key there is watch the degrees. If anytime the top is larger than the bottom, or even the same, right, you got to do long division first. What you're trying to create is something where the bottom is bigger. Then you can usually do the integration. All right, so that's 5. There was another question about 7. So this is what I was talking about at the beginning. So actually, I think theirs was the exact same problem. Okay. So you don't need to reinvent the wheel here, right? I mean, like I said, if you watch that video on where these things come from, that'll kind of give a rough idea of like how we do these things. But anytime you see a trig function all by itself, right? One trig function, no power, nothing crazy, right? The basic 6 trig functions: sine, cosine, tangent, secant, cotangent, cosecant. we can use the cheat. Now, one thing you might want to keep in mind is if it's one of the other ones, like the other ones, I always think of like sine and cosine are the easy ones, right? Because they just cycle back between each other. The other ones all by themselves, remember, involve some sort of natural log, and that's why we didn't do them in Calc 1, okay? So again, you can think of it this way. You might want to try to memorize this. I mean, it's not a big deal if you don't, but trust me, it's going to maybe make your life easier later. But think of it as it's secant of whatever the inside is, and then you got this. So basically what it's going to be is the natural log of secant of that inside x over 4 plus tangent of x over 4 plus c, right? So you can jump right to that, right? The integral of secant of whatever is going to be the natural log of secant whatever plus tangent of whatever. So it's basically secant plus tangent. But the key here is the one thing you do have to remember is there's a complicated inside. So technically, the derivative of the inside would be 1/4, right? And you can use that trick with basically you're avoiding a u substitution, right? Because technically you have a complicated inside, you could make a u substitution here, but trust me, you're going to want to get in the habit of not having to make a u substitution here, right? Because this right here is going to be one step and like, again, a 90-step problem later. You don't want to have to make a u substitution here. Your hand is literally going to fall off in writing so much if you need to make a u substitution here. So it's kind of that same trick I was talking about in the previous problem here. Sorry. Yes, you have a complicated inside here. As long as the derivative of the inside is a constant, in this case, it's really easy to 1. But even in this case here, the derivative of the constant is 1/4. Just think about that. You're undoing the chain rule. So if chain rule normally you would multiply, then you would just divide by it. But dividing by 1/4 is the same as multiplying, right? And so basically think of it as where this came from is you were dividing by that 1/4. Right? So think of it as anytime you have a complicated inside, as long as the derivative of the inside is constant, you can then divide by that, right? I mean, think about that. If you were to differentiate this, right, the derivative of the inside would be a 1/4. So you'd have to multiply by 1/4. That's why this 4 is here to cancel off that 1/4. So there's no extra constant. So you can think of it that way too. But trust me, that's a trick you want to get used to. As long as the derivative of the inside is constant, just divide by that. Okay. Then 8. I believe this was another trig one. Yeah, I think they had a different number, but it's basically the same problem. So their number was 7, but whatever. It was cosecant of the t squared all over cotangent. I mean, the one that I have is the 4. And the one that somebody was asking about was a 7. Not going to change the problem. I mean, it's going to change the answer a little bit, but whether it's a 7 or a 4 or an 8 or whatever, the constant is just going to come along for the ride. It's not really going to affect anything as far as how you integrate this. Okay, so when you see something complicated like this, yeah, meaning there's a lot of tricks floating around, right? This is one where you might be thinking, hey, maybe I could somehow simplify this. Okay, now how you simplify these is kind of up to you. There's lots of ways. I mean, I don't know if you remember, but like, you know, when you took trig back in the day, hopefully you remember like those trig identity problems. Usually it was like a really complicated bunch of trig equals something usually simpler. And remember you had to use all the properties to make one side look like the other, right? It's kind of what we're talking about here, if that's ringing a bell. But basically, complicated. I want to use some trig identities to make it look simpler, right? It's kind of analogous to complicated, can't integrate it, do some algebra to make it look simpler to like get to something, right? And that's what Calc 2 is all about, really. It's you're trying to integrate something complicated. The majority of the work is making it or transforming it to something else that I already know how to integrate. That's pretty much, well, that's the huge chunk of what Calc 2 is all about. The problems, they just get harder and the transformations get harder, but it's all about transforming it to something else. Okay, so I don't know how to integrate this. Got to transform to something else. They got to play around with these things. Worst case scenario, if you see trig functions floating around, you can always go back to sine and cosine if you like, but trust me, you might want to get in the habit of being able to work with not just sine and cosine, because again, they're going to get longer and crazier. But a couple of things should be popping out at you in terms of especially there's a squared floating around. Anytime you see a trig function with a squared floating around, that same form is used. Remember, Pythagorean identities are really great with squareds. Okay, remember the basic one everybody remembers usually is sine squared plus cosine squared is 1. It's basic one. But when in doubt, especially like, yeah, you got this sheet, sure, but honestly, it's not that hard to get to the other ones. What I mean by that is think of this equation here. If I were to divide everything by a sine squared, so like sine squared divided by sine squared would be the 1, and then the cosine squared divided by sine squared is cotangent, and 1 divided by sine squared is cosecant squared, right? And the same thing, this one comes from dividing this by cosine squared. Like cosine squared, divide this by cosine squared, divide this by cosine squared, right? So really, these are all three saying the same thing. They're just in different forms. But this one would be great here, right? That's what I have is cosecant squared, right? So I can turn that cosecant squared into a 1 plus cotangent squared. Okay, so the 7, whether you leave it there or pull it out, it's entirely up to you. But the cosecant squared, I can turn that into a 1 plus cotangent squared, t, whatever. And then the cotangent, t. But now I've created two different terms here. So it's that usual, there's only one term on the bottom, but 2 on the top. You can divide it into each one. So I could think of this as 7, and this is like 1 over cotangent t plus the cotangent squared t, and then cotangent. Right? 1 over cotangent is basically going to flip cotangent, so that would turn that into tangent. And then here you can get rid of a cotangent, right? There's 2 of them on the top, 1 on the bottom, so that's only one of them. Now I'm separated by addition, so I can do each one individually. So again, that 7 is going to come along for the ride. And now we've got tangent all by itself. Once you got a trig function all by itself like that, and you're integrating, you can jump right to this, in this case, the negative natural log of cosine t. But again, hopefully you can almost kind of visualize tangent is sine over cosine, right? The derivative, I mean, like in your head, I know it's expecting a lot. If you're in Calc 2, I would expect you could look at tangent in your head, be able to see sine over cosine and say, hey, look, if I were to make a u substitution, the derivative of cosine is sitting right there. It's a 1 over u. And then when you integrate that is the natural log of the inside. Watch out for the derivative. Should you be able to do that all in your head? Yeah, you really should, right? At this stage. The same thing with cotangent. Yes, you have the sheet here, right? You could do that. But again, hopefully you can visualize cotangent is cosine over sine. But again, it's that same trick. If I let u be the bottom, the derivative of the bottom is sitting right there. So it's just going to be 1 over u. And so that's just going to be the natural log of u, but the inside was the sine t. And plus c. And there you go. Again, you're more than welcome to leave it like that. I don't care. But do notice that you do have 2 logs. One's being subtracted and the other one's positive. So you could use those log properties and put them together. So you could think of this as 7 natural log of the absolute value of, this is the negative one. So this is the one that will go on the bottom. So this would be sine t over cosine t plus c, which then you could switch that back to sine over cosine, which is the tangent. Right. So again, you could do that. Which one's better? I don't know. It's a matter of opinion. They're both correct, right? This is obviously easier answer to look at, to type in, whatever, but both would work there. Okay. All right. Another one. Oh, there was a question about 9. So I wanted the main thing is I just want to make sure we get the directions here. So I want to find the general solution of the differential equation, then use a graphing utility, blah, blah, blah. And you want to find the particular solution that passed through the given point. And then don't forget the absolute values were appropriate. Okay, so the one that I was asked about was dy dx equals x minus 10 over x. And it was going through the point -1, 0. Okay, so first off, what are we talking about here? So what this is saying is you're trying to find the general solution of this differential equation. Or remember, what you're trying to do is find the original function. So you're given the fact that the derivative of some function, what is that function? I don't know. That's what we're trying to find, right? Think of y as the original function. I don't know what the original function is, but I do know that the derivative is what was given here. Okay, so let's work with that. So basically what I'm saying is if I know that, I'm trying to find what the y was, right? But I know that the derivative is this. Well, think of it as if I don't know what a function is, but I know its derivative, you could anti-differentiate it, right? Or if you wanted to get a little fancier with this, you could think of this as dy equals x minus 10 over x dx, right? So you're moving the dx over, and then you could integrate both sides. And the integral of basically 1 dy would just be y. And so ultimately what you're after is you're just trying to integrate this function. Right? And so that's the idea. So basically what it boils down to is it's a fancy way of saying find this definite integral to start with. Indefinite integral because there's no bounds, right? So it's just another way of saying it. Okay, so how do I integrate this? Well, again, it's got that usual, see the degree of the top is 1, the degree of the bottom is 1, so the degrees are the same. So anytime you see that, you want to do the division. And since there's only one term in the bottom, you can actually divide it into each one of these, right? So you can think of this as like x over x minus 10 over x. Then it's basically be 1. Not much I can do to simplify this one. Okay, now I've separated into 2 separate problems, right? So this one all by itself would just be x, and the 10 comes along for the right here, and the x all by itself on the bottom like this, since it's a power of 1. Don't make sure if it's a power of 2 or 3 or 4, then you would move it up, make it a negative power. Use the power rule. But since it's a nice linear term, not a higher power, that's why we can use the natural log plus c. So basically what this is saying is my original function y is this. I probably should write, but this would be what's known as the general solution. It's called the general solution is because I don't know what this particular value of c is, right? So if you weren't given that point and it just said find the general solution, this is in general all of the family of functions, because the constant could be anything, that would have this as the derivative. But I don't want that. I want the particular one that's here. So in order to find the particular one, this is saying if I plug -1 in for x, you better get 0 out, right? So basically what I'm saying is you plug 0 in for y and you plug -1 in for x, right? So that it goes to that particular point. So that means 0 equals -1 minus 10 natural log of absolute value of -1 plus c. And now the goal is find the particular value of c that will make this happen, or basically find the value of c. So this would be -1 minus, now here, well, I probably should write the whole thing. The absolute value of -1 really is 1. And then the key here, the natural log of 1, when in doubt, maybe think of it as the natural log of 1. That's what we're trying to find. But remember, how do you find the natural log of something? I mean, okay, can you plug this in the calculator? Yes. But trust me, this is one you want to stick in your brain and not have to pick up a calculator every time. Again, you can all of this stuff later is going to be small parts of a huge problem. Remember what natural log means. It means e raised to some power gets me to 1. Well, the only way you could take just about any number and raise it to a power and get 1 is if that power were 0, right? Something raised to 0 power is by definition 1. So basically that means this is 0. So this goes away. So 0 would equal -1 plus c, or basically c is 1, right? When you move the 1 over. So now again, this is not the answer. The answer is this whole function. The answer is the equation, or the whole original function, y equals x minus 10 natural log of the absolute value of x. But now we know this particular value of c to be 1, right? So that's the actual particular solution. Okay. Also, don't forget when you type it in, don't forget those absolute values, right? That's what I was talking about on the problem. So there's 9. Another one was 10. So 10 is basically the same idea, but it's just a little bit more complicated. One that I was given was 6 over x squared, not 3 over x squared. And it was given that f prime of 1 was 6, and f of 1 was 4. And then it did say x is greater than 0. Okay, so it might be nice to see it in here first before we go to the paper. So again, find a particular solution. Same thing as before, right? So finding a particular solution here, or forget the particular in general, just finding the solution means finding the original. So like with 9, you were given the derivative, or really the first derivative. So you'd have to anti-differentiate it to get to y. Okay, back to the original. Here, you're given the second derivative. So what that means is you would have to anti-differentiate twice to get back to the original, right? So if I'm given the second derivative, I can anti-differentiate and get back to the first, and then anti-differentiate again to get back to the original. But don't just do that. Just go, oh, the second derivative, the first derivative, and the original, bam, bam, bam. Because remember, every time you anti-differentiate, you got to have a plus c. So when you go to that first derivative, you anti-differentiate, it's going to have a constant on it, right? With a particular value. When I anti-differentiate it again, that constant is going to be a constant times x now. And then another constant is going to come in, right? So what I'm saying is do it in stages, okay? So, and that's kind of why they give you two different values here. So we break that down. So forget this stuff for a minute if you're not with me on that. Let's go through the whole thing. So here's the second derivative, okay? So what I'm saying is, what would the first derivative be? The first derivative would be the antiderivative or the integral of this function, right? This is the second derivative. If I anti-differentiate it, it should get me to the first, okay? Now here, don't use natural log here. This is the other part about this new stuff, the natural log, because I mean, you're using it's new, so there's keep testing on it. So you're using it, but don't abuse it either. Remember that natural log thing only comes in when the power rule doesn't apply, or it's a linear term in the bottom. It's not what you have here, it's a squared, which means this is really a Calc 1 problem. You want to think of it as move it up, make it a -2 power. Then you can use the basic power rule, right? So power rule, you would add 1, which is -1, and then technically divide by -1. Or in other words, your first derivative is really -6. And if you want just to make it look nicer, you can move this x back down, plus c. Okay. But now, remember, there's a plus c. So don't just jump to the original function yet. They told me that if I plug 1 into the derivative for x, you better get 6 out. So the goal is to find the value of c that would make this happen. So if I were to plug 1 into the derivative for x, it'd be -6/1 plus c, but I better get 6 out for this particular problem. Or in other words, c would be 12, right, when you add 6. So what that means is my first derivative is really -6/x plus 12. Now we just do it all over again, right? So if I know what the first derivative is, now I just need to find the second derivative. I mean, sorry, go back to the original, right? They gave me the second derivative. So we went from the second derivative anti-differentiated to the first. So now the original would be the antiderivative of this function. Right? Okay, so this one you can do each one separately, but now here, this is a linear term in the bottom. So now this would be the natural log of the absolute value of x. And this would just be straight 12 plus x is c. So there's my original. But now we can find that particular value of c using this new information, because they told me it's in here. F of 1 is 4. So in other words, if I were to plug 1 in, so -6 natural log again of 1 plus 12 times 1 plus c, you better get 4 out, okay? Again, natural log of 1 is 0. This is going to go away. This is basically 12, so you subtract off 12, so c would be -8. Okay, so then what does that mean? Your whole original function here, right? This original function here would be the -6 natural log of the absolute value of x plus 12x, but now we know my new constant is the 8. There you go. And again, you're more than welcome. You can leave it like that. But one thing I should mention, it does say this x is greater than 0. Why is that there? Well, it's not a huge deal, but all that's basically saying is x is greater than 0. Then you know the absolute value is going to be the same. So in this case, you could drop the absolute value because x can't be a negative, right? It told me that, right? It also can't be 0 anyway, because, I mean, you couldn't divide by 0 to begin with. So you don't really need to use that. It's just there. If you wanted to, you could drop the absolute value. Okay. So that was 10, and then the last one was 13. This one was exactly the same. Yeah, they even gave you the picture. So I want you to find that area again. This was on the review sheet. And it's not going anywhere. But it's all, finding an area is now all about a definite integral. So a definite integral, gives you the area from the graph to the x-axis, which is exactly what they want. So finding the area, looking at that picture, it's a fancy way of saying we want to integrate 1 plus the natural log of x cubed over x dx. But now there's bounds, and they pretty much gave me the bounds, right? It starts at 1, goes to 9. So my bounds are 1 and 9. So basically the goal is to find that definite integral. Okay. So the question is, how would I do that? Real quick, I do this part here. I'm going to talk about this part here. Make sure you guys realize, and it's going to make a difference in what you see. There's a big difference between saying this, this, and really this. Well, technically, there's no difference here, right? So if you don't see parentheses like this, it's assumed that you're talking about the parentheses being there. But now if the parentheses are on the outside, whoa, this is totally different. What I mean by that is this is saying you're taking a number, cubing it first, getting an answer, then taking the natural log of the result. This is the same thing. These are actually equal. This is totally different. This is now saying, don't cube it first. Take the number that you're plugging in for x. Take the natural log first. Take the result of that and cube it, right? So there's a big difference there. So you have to pay attention to what the parentheses are. Now, if that power is inside the natural log, or in other words, it happened first, then basic log properties apply, meaning you could bring this 3 down if you wanted. Okay, here, this is totally different. Do not do this, right? That doesn't work here, right? The power has, I mean, basically think of it as the natural log has to be completely on the outside. So what you're taking the natural log of has to have a power on it. If it does, then you bring it down. But if the power is on the whole thing, then natural log doesn't apply because all that's inside the power, right? It's got nothing to do with the log. Basically, it's just a thing that's got a cube on it, period, right? So watch out for that. Okay. So this particular problem, oh, look, the cube is inside the natural log. So you could use those log properties, right? But first off, before you do that, you might want to notice it's that usual same thing over and over again. Only one term on the bottom, which means you can distribute this, right? So you can think of this as like 1 over x plus the natural log of x cubed over x, right? And then usually what I do when you see a problem like this, let's forget the bounds for a minute. We'll come back to the bounds later, right? I mean, we just have to anti-differentiate this, and then we'll worry about the bounds. Okay, now we can do these separately, right? Because I use separated by addition. That one's easy. Again, 1 over x is pretty much definition, natural log of x. This one is not so much. So here we're talking about the natural log of x. At this stage, it might be, hey, wait a minute, I can bring this 3 down since it's inside. All right, now, this is one of those, once you see it, it's crazy easy. But if you don't see it, you could be there all day, okay? So you have both x's on top and bottom. So it kind of has like a quotient rule feel to it. Remember, there is no quotient rule for integration. There is no chain rule. There is no product rule, right? If you're talking about derivatives, no matter what the functions are, it doesn't matter. If you see x's both top and bottom, quotient rule will work. If you see x's times each other, product rule will work. If you see x's inside of something else, chain rule will work. Integration, anti-differentiation just doesn't work that way, right? That's just how it behaves. So remember, the only way to do integration at this stage is you have to change the way it looks to make it look like something that we already know how to do, or use substitution. Now, one thing I do want to mention about use substitution, you want to get used to, okay, let's try this. Whatever. Or let's just run with that. Okay, so I just making up these problems, but when you see something, maybe let's do something like this, I don't know, right? Because you might be thinking, like, if that were not there, you could then just distribute the x squared, and then it would just be individual terms. But what if it was a crazy power to it? You could multiply this all out, but that's why I made it so big. You don't want to do that, okay? But the point that I'm trying to make here is, notice there's an inside here, but what is the derivative of that inside? The derivative of that inside, yeah, technically is a negative 3x squared. But the point is the derivative of the inside is x squared sitting right there, right? The same thing with this one. If I think about the derivative sine x, the derivative of sine of sine is cosine, is sitting right there, right? The same thing with here. If I were to talk about the derivative of the square root of x, one thing that might help is this is 1/2 power, right? So the 1/2 would come down, and then you subtract 1. But a negative power is the same as it's on the bottom. 1/2 power is the same as the square root. So the derivative of this piece is sitting right there. right? So that's the idea I'm trying to get to is when you see a complicated problem where it looks like a product rule, it looks like a product rule, it looks like a quotient rule field, but anytime you see a situation where one of the pieces derivative is sitting right there, one of the pieces derivative, one of the pieces derivative, that's when a U substitution is really helpful, right? Because that's the whole point. You would let U be part of it, and the du dx relationship is sitting right there, right? This one you can go either way. Okay, so that's what you want to get used to when you think of U substitution is the derivative, and but you got to be able to know it before you actually make the substitution, right? That's the whole point. Because if you notice here, what is the derivative of natural log? Oh, wait a minute, the derivative of natural log is 1 over x, which is sitting right there, right? So the point here is if you let u be ln x, then the du is 1 over x dx, which indeed is sitting right there. Okay, so basically this 3 is just kind of going to come along for the ride. The natural log is going to turn into u, and this x in the denominator along with the dx is just going to turn right into du. So ultimately you're just left with 3u squared over 2, and then technically plus c, right? And then you would resubstitute. But remember, this came from 2 different pieces. So really this is the natural log of the absolute value of x plus this piece here, which is 3/2 u, which is the natural log of x when you resubstitute squared, and then technically plus c. But hold on. Right, so you got to be able to recognize that U substitution is helpful because the derivative of one piece is the other piece. Okay. Also, make sure you watch out the difference between these two. This cubed is inside the natural log. Power rule applies. This squared is not inside the natural log. It's like I was talking about a minute ago. This is outside. Power rules do not apply, right? So don't bring the 2 down here. You can't do that. It's multi what I'm saying. But remember, there are bounds. So instead of a plus c, now you would use the 1 and the 9. And then from there, you just plug and chug, right? So if you plug in 9, you're looking at the natural log of 9 plus the 3/2 natural log of 9 squared minus, and then plug in 1. Natural log of 1 plus 3/2 natural log of 1 squared. Right. And then the key here is natural log of 1, 0 goes away. Natural log of 1 is 0 goes away. And there you go. Natural log of 9, not a pretty number, right? Because remember what natural log of 9 means is e raised to what power gives me to 9. Remember, e itself is not a nice number. So if I take a power, this power is not going to be a nice number. So you could just leave it like that. Right? Because all that goes away. You can throw in the calculator to get the decimal version if you wanted to, but why? I don't know. Why bother? Here's your answer. You're done. It's whatever number that is. But there's nothing you can do to simplify that, right? Well, I guess technically you can factor out a natural log of 9, but whatever. That's up to you. So that's what you would plug that whole thing right into here. Okay. One thing I want to mention about WebAssign. How do you know whether they want the whole answer like this with crazy natural log numbers floating around, or they want the approximation? Context clues. If it had said on here, round your answer to blah, blah, blah decimal places, then sure, then they would say, okay, that means throw in a calculator. But it doesn't say that. So it doesn't say that, they're kind of hinting on the fact that they don't want the approximate, they want the whole answer. So type it in like this. Okay. All right. So there you go. And then just let me know if you have any other questions.